Okay, we're at the end of chapter 4, which was on the graphs of the trig functions. And the final section is on harmonic motion. Now, harmonic motion is something that we study in detail in physics and engineering, so I don't plan to go into harmonic motion in great detail in this course. However, let's go ahead and roughly go through this section just so you can get a feel for this application of trig functions. All right, so simple harmonic motion, that's the most basic form of harmonic motion. And the way you can think about what that means is, so you can still have harmonic motions with functions that involve sinusoids, sines and cosines, but you can apply modifiers, and we'll see an example of that on the next page, and to where it still involves sines and cosines in the function, but it's just not considered simple anymore. And so if we look here, if you have like an ideal spring and you pull it, it's just hanging, the weight is just hanging, and then you pull it away from equilibrium and release, then it's going to oscillate back and forth, right? And so we get into detail in this in vibrations in engineering. We study this in depth, but also in just a general physics course as well. And so it's oscillating back and forth, right? And the simple harmonic motion case is the case where the spring is frictionless, so this doesn't damp out. It just oscillates at that same amplitude that you pulled it back. It's going back and forth forever and ever until something, according to Newton's laws, that everything's going to continue with no friction. Things are going to just continue to move forever until something stops it, a force stops it, right? So that's the idea of simple harmonic motion. And in vibrations, you start by modeling this with what's called a differential equation. And so not to confuse you too much, but you learn in calculus, differentiation and integration, and then after calculus, you get into differential equations. And so you can write this, what's happening here with a differential equation, and then when you solve the differential equation, what comes out of it is sinusoids. And for the case where there's no friction, it's just going to be the position of the weight as a function of time is just going to be sinusoidal. It's going to be oscillate like that forever and ever. Now, up to this point, I've been mentioning how, the sinusoids are so important because, it's like they're like the king of periodic patterns, right? Well, this is another example of that. A spring is like inherently mechanical. In engineering, you can model like even a piece of metal, okay? Like a metal rod, when you pull it, it responds like a spring, but it's an extremely stiff spring, but it has this, the idea of a spring is that the force on the spring is proportional to the displacement, linearly proportional. That's the idea of a spring. Well, it's the same thing when you pull on a metal rod. It deflects linearly, but it's just an extremely high K value with metal as opposed to a spring, which is kind of designed to deform. And so it might not be apparent to you, but a spring system like this is like inherently part of mechanics and physics and the world around us. You can model a lot of phenomena with like a spring-like nature. And so it just goes to show you that, the fact that if you pull a weight and you let it oscillate and you release it and it oscillates, it's going to follow a sinusoidal pattern, the position of that object. That's just another indication of how hugely important sinusoids are in nature. Okay. And so, but yeah, if friction is neglected, then it's going to be just the position as a function of time. Okay, so y as a function of time is just going to be a sinusoid with a phase shift. And that's called simple harmonic motion. Now, again, what we're going to see in a second, you could apply for things that deviate from simple harmonic motion, which is everything in nature, right? Because everything is damped. Nothing just oscillates forever. You can apply modifiers to the sinusoid. It's still harmonic motion, just not simple. Simple is just you're going to have so the most general way to write a sinusoid is a constant, and I'll pick sine, okay, then another constant times the variable, well, okay, in this case it's time, plus a phase shift. That's the most general way to write a sinusoid. Well, in this case, it's sine. you could write cosine the same way, but you can show that, and I mentioned this in another video. You might say, well, which one do you pick, sine or cosine? It doesn't matter. Like you can combine any non-shifted sine and cosine. So with no phase shift, one non-shifted sine plus one non-shifted cosine is going to result in a shifted sine or a shifted cosine. Like these sine and cosine are one and the same thing. So you can write this as a sine, as a cosine, a shifted sine, shifted cosine, or a sum of a non-shifted sine and cosine, whatever you want. Okay, so other applications of this type of motion include sound, electric current, and electromagnetic waves. This harmonic motion, right? Because you have sound waves, electromagnetic waves. A wave, think about a wave in the ocean, right? Sinusoidal. Okay, to develop a general equation for such motion, consider figure 47. Suppose that point pxy moves around the circle counterclockwise at a uniform angular speed omega. Okay, so yeah, we've seen this problem already, like a couple of chapters ago. Now, the way they're presenting this, though, I find a little confusing because we're developing this equation, they're saying, but the harmonic motion equation, it comes from a differential equation. You model the spring system with a differential equation, and it makes intuitive sense when you do this, but you have to understand derivatives and all of that first. But it makes intuitive sense. Like you would say that, okay, if you were modeling the motion of a vehicle, then you might say that, okay, it is, you're going to put the forces on it. You're going to use Newton's second law and put the forces on it. Well, you have the force from the tires. The tread on the tires is, let's see, like m, the mass of the vehicle times the acceleration of the vehicle. Then there's a force opposing that. That's the drag force from the air. So it's going to be some constant k, and drag force is a simple way of modeling them is they're proportional to the velocity. So the faster the velocity, the higher the drag force, right? From wind. Okay. Now, if the car is traveling at constant speed, then you set this equal to 0 because there's no acceleration, right? So it's like the force pushing the car from the tread on the tires subtracted from the drag force, it results in the car isn't accelerating; it's moving at constant velocity. And so, okay, but acceleration is the derivative of position with respect to the second derivative of position with respect to time. And velocity is the derivative of position with respect to time. That's a differential equation. And you solve it by solving for, you want to find what x of t is. Okay? And when you do this similar kind of setup with a spring system, then you solve the differential equation, and what comes out of it is a sinusoid. And all they're talking about here is, when we, at the beginning of this chapter, or no, it was maybe in the previous chapter, but we looked at sinusoids and we identified what the amplitude was, the period, the frequency, the angular frequency, right? So we know that any sinusoid is going to be intimately associated with a circle, right? Your position on a sinusoid, you can kind of track that with a corresponding position on a circle, right? Remember that you could only do this, only works out this way with sine. Well, I think you could do this with cosine as well, but like you have to line them up horizontally maybe or vertically. But the idea is when you're going around the sine curve, the vertical positions around the circle are lined up, and that was the only periodic function to where it worked that way was the sinusoids. Any other periodic function, it didn't work that way. Okay, and so all they're talking about here is the relation between the sinusoid and the circle. But if we're going to think about if what comes out of that simple harmonic motion, that spring system, okay, if what comes out of that is a sinusoid, Well, then we already know how to write this out. So it's going to be, well, let's say where they put a sign here. Let's see. Well, okay. Well, they illustrate with both cosine and sine, but again, you could create a shifted cosine or sine if you wanted to, but but any sinusoid. Let me make it shifted. So well, okay, this has a period, this has a amplitude, but then the frequency and the angular frequency, those are like married to the period. So once you set a period, then you've automatically set an angular frequency and a frequency. And when it comes to harmonic motion, you'll typically see it written in terms of the angular frequency. That's how it's written for some reason. But you could write it however you want. So omega is the angular frequency. So if we were going to do that, then, okay, we know that we've got, so I'll just say, I'm not going to say X or Y, I'm just going to say the position. Well, no, we'll say Y. Let's say we'll come here and say Y. So the position of once you release the mass and starts oscillating is going to be, so whatever the amplitude is, because it's oscillating about the equilibrium position, so it's not shifted. The sinusoid is not shifted vertically. And we can use sine or cosine. Let's use sine. Okay. Now we're going to scale the period, right? And based on angular frequency, if you remember, so okay, the amplitude is going to be like in meters, like the position, right? It's like the position in, or some unit of distance. Now the angular frequency is going to be, that's radians per second. If you don't remember what angular frequency was all about, go back to those sections. We went through that in great detail. Okay, it's going to be radians per second, and it's just saying that. So when you go a full period is going to be in time, right? This is position as a function of time. This is y, this is time. So the period is going to be a certain number of seconds, but you go 2 pi radians in that number of seconds. So omega is going to be 2 pi over the period. Okay, now let's say we just had some constant here in front of the t. Okay, and then we'll put a phase shift. Okay, how does b change the period? Well, we know it's like multiplying 1 over b times the standard period of sine, which is 2 pi. Right, so the new period in this case would be 2 pi divided by b. Okay, so if we solve for b here, you get 2 pi over p, which is omega. So what they do here, they just replace that b with omega. But you could also write it, I think, like you could do t divided by the frequency instead. That'd be fine too. But they write it like this. And again, the phase shift is just going to be, so if we're doing sine, the phase shift would be this. Okay, and so, but this is simple harmonic motion because it's just oscillating back and forth with no damping. It's just a sinusoid oscillating back and forth about an equilibrium position. Now, it's not just any oscillation, though, because you could oscillate with a square wave about an equilibrium position. Right? It needs to be sinusoidal, and it's the case when you solve the differential equation for a spring, like an ideal spring system, it comes out sinusoidal. But they just specify, they don't go into this much detail. They just specify that you could, like harmonic motion, when you think about if you had a constant angular velocity going around like if this point P was going around the circle with a constant angular velocity, then if you tracked the x position as a function of time, because there's a velocity here, right? That would be harmonic motion about the y-axis, simple harmonic motion. And then if you track the y position, it would be the same idea. It would be simple harmonic motion of the form a sine omega t, where a is the radius of the circle, and a cosine of omega t, where that would be the x coordinate. The x position would be simple harmonic motion. The y position would be simple harmonic motion, and that's what this is, because this is modeling this, right? This is going back and forth around the equilibrium position. You can still have simple harmonic motion with a shifted sine curve, right? The shift is just telling you where you happen to start or something. It's kind of like the initial condition, okay? Now, but I think it was earlier in this chapter, or whenever we went through the sinusoid graphs and identified the frequency, the angular frequency, and all of that. I gave you what I consider a very useful tip, in that these concepts of angular frequency and frequency, right? They're talking about the frequency here and the angular frequency and the period. Typically, you don't talk about angular frequency and frequency outside of a sinusoid that has the independent variable being time. If it's something else, you don't really hear it mentioned that much, angular frequency and frequency. And I think they shouldn't do that, because what happened to me is the whole idea of the intimate relation of a sinusoid to a circle got lost on me. And so just remember this omega in this in the frequency, right? The frequency is just, you have cycles, one cycle per period. That you can still think about for some sort of sinusoidal pattern that's not a function of time. It could be a function of whatever. You can still think about the idea of the frequency, right? And the angular frequency and that tie to the circle. In fact, I would suggest that you do that. Anytime you see a sinusoid, no matter what the units are, like that's why I gave examples with those example problems where we had these weird horizontal units that had nothing to do with time, and you could still specify the period in those units, the frequency, one cycle per, what was it, like number of skateboards sold. That's the period. The angular frequency was like 2 pi, or whatever radians per skateboard sold, right? You can still think about it that way. Anytime you see a sinusoid, you can think about these concepts and its association with the circle. And also note that, I tried to stress as well that even if you had a shifted sinusoid that was shifted vertically, well, that still has an angular frequency, a frequency. It's not like just because it's shifted, that doesn't mean that all of a sudden you can't think about frequency and angular frequency and period. No, you can absolutely, it's any sinusoid has these properties. Okay, so now they do some example problems. We're not going to work any example problems on this topic, except for we're actually going to go into that London Eye Ferris wheel problem again and think about it in terms of modeling it as a function of time, just so you can get a look at that, and we'll use an equation like this, sine or cosine of omega t. Okay, but if you look here, though, they go from simple harmonic motion to damped oscillatory motion, and this is still, I think, they still call this harmonic, just not simple. Not sure, but the idea is that this is more realistic in the sense that, well, we know that like a spring damps out, right? So we would expect a spring to actually, let me do this, a spring to actually do, right? Well, this is still, you can still model this with sinusoids. And all you're going to do is, so you see they apply an exponential decay multiplying the sinusoid. So the e to the minus x is like, and so that's what gives you that damping. So and it goes further than that, right? You can, all of the most complex engineering and physics problems, to me, I used to always think that, it was hard for me to get motivated when we were studying things that seemed so trivially simple. In my mind, it was like, well, the real world's not this simple. So how could I use this to model something in the real world? And that is true. However, what I didn't realize is that we were learning the fundamentals. The more complicated problems are built off of the simple things that you learn. So if you understand the simple harmonic motion, then you can add to that. Like we haven't gone away from simple harmonic motion here. It's still kind of at the foundation of this. It's just there's modifiers applied to it, and you could add more modifiers if you wanted to even refine this to be even more accurate. Okay, so now let's get started with chapter 5.